Okay, so I think we did up to this point, right? We have to start. Where we have to start? We did the exponential functions, as I can remember, and also we did these examples as well. And I ask you to try these ones. Now I think we have to start with finding equations of exponential functions. We have to start from here, right? No, we did this one as well. 2.4492 we did. I can remember that one. Now we have to start with the compound interest. You can hear me, right? Hello. Can you hear me? I think your mic is not working. Maybe it's not plugged as well because your mic is not appeared. Hello? Now your mic, you can unmute your mic. Yes, hello, you can hear me, right?
Yes.
Okay, great. So let's start from here. I think we have to start from the compound interests. So were you able to go through with the rest of the examples of this fourth unit?
Yes.
Okay, then we'll start with the compound interest. So for this compound interest, um, I think you will have learned this. Learned means heard about the compound interests. So here in the bank certificate of deposit CD example earlier in the section we encountered compound interest because earlier also we talked about compound interest. Compound interest means, let me get this one. Compound interest means so we deposit some amount and then at the end of this year we will get an interest. So for the interest of the second year, then this initial amount plus interest, the total amount will be the deposited money. This one we consider it as the total deposit money. And then for this amount, we will be calculating the interest. That's what for the compound interests it happens. Is it clear?
Yeah.
Okay. Typically, bank accounts and other savings instruments in which earnings are reinvested, such as mutual funds and retirement accounts, utilize compound interest. So the term compounding comes from the behavior that interest is earned not on the original value. This is not calculating for the original value. This is calculating for the accumulated value which is available in the account. That's what here they have mentioned, accumulated value of the account. So in the example from earlier, the interest was compounded monthly. So we took the annual interest rate, usually called the nominal rate or annual percentage rate, that is APR, and we divided by 12. So if you can remember, you just asked me now why we were divide that annual interest rate by 12 as well, Kayla? Because that is because to get a monthly rate, what we did, we just divide that total annual interest rate by 12 and then we just calculate the monthly interest. So the exponent was then measured in months. So the exponent was measured in months. Generalizing this, we can form a general formula for compound interest. Now, if we generalize this entire theory, we can form a general formula for compound interest as well. If the APR means annual percentage rate, if that APR is written in decimal form as R and there are K compounding periods. Now, this example, we are talking about the bank deposits and the bank interest rates for the compound interest. The domain is the banking industry, okay? So there we are going to consider kind of a new formula. We are generalizing this entire theory. We can form a general formula for compound interest if the annual percentage rate is written in decimal form, that is R. So the R is the what we call they are the APR, that is the annual percentage rate, and we have K, and there are K compounding periods. Okay, define the compounding periods per year, and then the interest per compounding period will be calculating by R divided by K. Likewise, if we are interested in the value after T years, if we are calculating the total value after T years, then the formula will be A times, A means the initial value, what we deposited there, okay, the starting account value, initial deposited value, A times 1 plus, now here the rate is R over K. So R is the annual percentage rate, that is APR. APR, we are given that kind of a what we call a new name, that is nominal rate, and K is the number of compounding periods in 1 year to the power of what? To the power of KT. KT. So again, K means the number of periods, and also here if we are defining, so T means actually the number of years. So this time of periods should multiplied by the total amount of years, that is T. So the equation for the compound interest formula will be A times 1 plus R over K to the power of KT. Is it clear? This is what they have given. Is it clear?
Yes.
Okay. Shall we go through with the example then? Okay. Now, what this example says, we'll do the example 8 together and you can try the example 9 then. So the example 8, if you invested $3,000 in an investment account, so the initial, how to figure these type of questions. So then the initial value A will be $3,000. Okay. If you invest $3,000 in an investment account paying 3% interest compound quarterly. Now the R is what? R is 3%, right? That's the rate, but the rate is given kind of a quarterly rate. So 3% means if I convert it into decimal, it would be 0.03. Now quarterly means per year, how many quarters are there? 4. Then K would be 4. Now, what is the question? 3% interest compounded quarterly. How much will the account be worth in 10 years? Now, T is what?
10.
10. Yes, they ask us to calculate the total amount which is available in our account after 10 years. So these are the values. Now what we need to do? We need to substitute all these values to the compound interest formula and find out the final total value. Is it clear?
Yes.
Since we are starting with the $3,000, then the value A is 3,000. Our interest rate is 3%. 3% means in decimal, we can say it as 0.03. And then the equation, so the interest is given per quarterly. So they ask us to calculate it quarterly, which means per year we have 4 quarters. That is K is equals to 4. Then they ask us to consider 10 years. That means the value T. The value for T will be 10. Then you can substitute all these to the compound interest formula and then calculate the final value. So the total value after 10 years, it would be 4,045.05 amount of dollars. Is it clear?
Yeah.
Okay. Can you try this example 9?
Okay.
Okay.
Mm.
What happened?
Oh, I got.
You got right?
Yeah.
Okay. The answer also correct, right?
Uh,
So
e-
the final answer, it would
oh,
be, they have given the entire working. The final answer, they're asking over 18 years, and she believes the account will earn 6% compounded semi-annually twice a year. How much will Lily need to invest in the account now? No? The final answer will be 13,801, this amount.
I thought A was 40.
To have $40,000 in 18 years. So, how it happens? A 529 plan is a college savings plan in which a relative can invest money to pay for a child's later college tuition, and the account grows tax-free. If Lily wants to set up a 529 account for her new granddaughter, wants the account to grow to $40,000 over 18 years. After completing 18 years on that account, she just wanted to have $40,000. Is it clear? After 18 years. So now what they are asking, and she believes the account will earn 6% compound semi-annually. 6% compounded semi-annually interest rate, which means semi-annually means twice a year. How much will Lily need to invest the account now? Which means we need to find out the value A. Value A means the initial amount. Now let's figure out. So the equation, if it's a compound interest related equation, then the amount, so the equation will be A times 1 plus R over K to the power of KT. That's the compound interest formula. Now we need to find out the value for A. A is the initial value. Now this value, this is what? According to the given context, AT is the final value. No? Final value means there they have given 40,000. So the output value, or the after completing 18 years on that account, she should have $40,000. So this is the final amount, or the output value. So R is the rate. Okay, rate is 6%, which means 0.06. But it's semi-annual. Semi-annual means per year we will be calculating the interest twice. That is, the value of K is 2. T means the number of years. So she just wanted to have $40,000 after completing 18 years, which means T is 18. Now you can substitute all these values to the compound interest formula and then find out the value for A. That's what we need to do. Okay. Is it clear for you?
Yes.
Okay. Then, okay, then try it now. Recalculate example 2 from above with quarterly. Okay. So, okay. If you are okay. So if we wanted to calculate the same question according to the if they have given us that this entire question will be for quarterly compounding here, then what are the differences we need to consider?
It will be like 0.06 out of 4.
Yes, yes, yes. So the value of K will be 4, right? Because per year we have 4 quarters, no? So then that would be the difference. So you can do this one as a homework. And because of compounding throughout the year with compound interest, the actual increase in a year is more than the annual percentage rate. If $1,000 were invested at 10%, the table below shows the value after 1 year at different compounding frequencies. If it's annually now, then here we have 1,100. Then if it's semi-annually, then we are calculating the interest twice per year. Quarterly, 4 times per year. Monthly, it will be 12 times per year. If it's daily, which means 365 times. That's how we normally calculate these ones. Okay. So if we were to compute the actual percentage increase for the daily compounding, there was an increase of this amount from an original amount $100,000 for a percentage increase of. So if we wanted to calculate the percentage increase of, then we need to divide this difference. The value which we increased should divided by the actual value, initial value, that is 1,000. So then we have that increase rate as 10.516. So we call this as the annual percentage yield. That's what we call it as APY. Okay, that's fine. Then notice that given any starting amount, the amount after 1 year would be, if it's 1 year now, then the t is equals to 1. No, t is equals to 1 means here we have kt. So kt means if t equals to 1, then this will narrow down to k equals to k because the value t is equals to 1. Then we can rewrite the initial compound interest formula as AT is equals to A times 1 plus R over K to the power of K. To find the total change, we would subtract the original amount, then we can find out the final value. So it's clear, right? To find out the APY, APY means the annual percentage yield, what we have to do. So we need to, the annual percentage yield is the actual percent a quantity increases in 1 year, it can be calculated per year how much it was increased. So then we can calculate that from this formula. So the t, value t is equals to 1. So from this, we are subtracting 1. That's how the normal APY, that is the annual percentage yield, calculated. Okay. Now we'll move to the example 10. Okay, check for the example 10 whether it's clear. Example 10. So what are the topics we need to cover on this one? So you just read the example 10 and try to figure out. I'll check whether I have completed all the theory notes. So in
So, wait,
uh,
so if the frequency increase, that means K is bigger.
so here bank A offers an account paying 1.2% compounded quarterly. Bank B offers an compounding paying 1.1% compounded monthly. If it is quarterly, then the K value K is 4. If it is monthly, then that means per year we have 12 months now. Then the value K is equals to 12. Okay, is it clear?
Just
Okay, you just do the question. When do you have final exams?
at my school, so only in September.
September, you have the final exams, which means we need to complete this entire uh, grade 11 book by September.
My school starts in September.
Starts in September. Okay, starts in September means, okay, starts in September. Okay.
I don't understand him.
You don't understand? Okay. So there. So first one is now bank A offers. Okay, here we have the bank A, here we have the bank B. So bank A offers an account paying 1.2% compounded quarterly. So the rate is 1.2% means 0.012. Then here also 0.012 with the compounded quarterly. Then the value K is equals to 4. For the bank B, here we have the rate as 1.1%, that is 0.011, and there we have K as 12, because they are calculating the interest monthly, compounded monthly. So which is offering a better rate to the customer. So we can compare these rates using annual percentage yield. For these kind of questions, what we need to do, we have to calculate annual percentage yield for bank A as well as annual percentage yield for bank B as well. And then what would be the best one? If the annual percentage yield is high, then that bank is giving the highest interest or the better rate, right? So then what we need to do, we need to calculate the annual percentage yield. How do we calculate the annual percentage yield? Annual percentage yield means per year how much we will be earning, right? So to do that, what we have to do, so the annual percentage yield is equals to What's the equation? 1 plus R over K. Since we are considering per year, then as the exponent we have K minus 1. Then for the bank A, we can calculate the APY, annual percentage yield. For the bank B, we can calculate the annual percentage yield. Okay? And then we can compare these two and what's the best offer? The best bank actually. The highest rate. The bank which has the highest annual per yield rate goes as the best bank. So if you calculate for bank A, there we have 1.2%. If you calculate the bank B rate, annual percentage yield 1, then there we have 1.1%. So the best one would be the one which has the better rate, that is bank A.
So the more rate mean
More rate.
interest is good.
Yes. Okay. Complete the question. I think we have to do the graph of exponential. Okay. Yes, we need to do these ones. You're done with that question?
Yes.
Okay. So the last theory part of this section, a limit to compounding. There also we have few limitations to consider. As we saw earlier, the amount we earn increases as we increase the compounding frequency. So if you check for the previous example, annually, we are calculating the entire interest only one time, then we are earning only 1,100. But if it's semi-annually now, then we are calculating the interest twice. So the interest has been increased, at least a small amount, that amount is increased. So the number of times we are calculating the compound interest getting higher, then the final value also is getting increased. So here, as we saw earlier, the amount we earn increases as we increase the compounding frequency. So the table, though, shows that the increase from annual to semi-annual compounding is larger than the increase from monthly to daily compounding. This might lead us to believe that although increasing the frequency of compounding will increase our results as well, there is an upper limit to this process as well. So here we have annually, semi-annually, quarterly, monthly, daily, hourly, and then uh, once per minute, once per second. So these values do indeed appear to be approaching an upper limit. This value ends up being so important that it gets represented by its own letter, much like how 5 representing the number. So what does this mean? Okay, what does this mean? To see this, let us examine the value of per dollar. Okay, per dollar investment invested at 100% interest for 1 year. If we calculate the same thing per annual, then after completing the first year, we have $2. If we are calculating this semi-annually, then after completing the first year, we have 2.25. Quarterly now, we have 2.44. Monthly, 2.61. Likewise, this one will increase. Is it understand?
Yes.
These values do indeed appear to be approaching an upper limit. This value ends up being so important that it gets represented by its own letter, much like how phi represents a number. So you can see now this one is narrowed down into a number 2.7182. So for this amount, we are giving kind of a special value, that is E. E is 2. E means actually closest to 2.718282. That's how we map this value E here. So Euclid's number, that is E. E is the letter used to represent the value that 1 plus 1 over k to the power of k approaches as k gets big. K means the number of times which we are calculating the interest. So make a very. So when the value k get increases, then this total amount getting much closer to 2.718. Okay, 2.718, and we give that amount as a number, that is E, like 5. 5 is 3.17, 3.1 to 3 point, as I can remember, 3.172 or something. Likewise, we are giving kind of a special value, that is E. E is 2.718282. Is it clear?
Why do we have that specific number?
So because for any kind of number, for any kind of situation, okay, so this one is kind of a constant. We can't say that it's kind of a constant because so we are only taking 6 number of digits, 6 number of digits. Once we increase these amounts anyway, so for any scenario, for any given scenario, for any domain, any given scenario, once we increase the k, all these equations will narrow down to value E. That's why it's kind of a special case. Because of that, we are giving kind of an we are initiating kind of a special value, that is E for Euclid's number, and also we called E as exponential. For exponential curves, E comes to the topic at that time. Okay? Is it clear? Is it clear?
Yes.
Okay. So because E is often used as the base of an exponential, that's why. So base of an exponential, most scientific and graphing calculators have a button that can calculate powers of E. We can calculate E to the power of 1, E to the power of 2, E to the power of 3, likewise. So exponential, most scientific and graphing calculators have a button that can calculate powers of E, usually labeled E to the power of X. So you can see this exponential one on your calculators as well, E to the power of X. Some computer software instead defines a function exponential, EXPX, that is exponential. That is exponential. EXPX. EXPX is equals to E to the power of X. On your calculator, you can see either E to the power of X or else EXPX. Okay? Then, because E arises when the time between compounds becomes very small, E allows us to define continuous growth and allows us to define a new toolkit function, that is E to the power of X. This one belongs to the calculators. Okay? Okay. Now we are moving to the next part. Continuous growth can be calculated using formula. You can calculate this continuous growth questions by using your calculators as well. A is the starting amount. R is the continuous growth rate. You can use this E and calculate it by using your calculators. Okay, you did it earlier as well. Okay, so the example 11. Can you try this example 11 now? Is it clear up to this point? No? Is it clear?
Yes.
If I
Yeah.
like doing it much fast, please stop me and tell me. Always you can stop me and ask anything. Shall we try this example 11 then?
Okay.
Okay. Radon 222 decays at a continuous rate of 17.3% per day. How much will 100 milligrams of radon 222 decay to in 3 days? You can just use this function. Fx is equals to a to the power of E Rx. For this continuous growth, you can use these ones. Yeah, try to do that one. For this week, you have kind of a big exercise. Section 4.1 is completed. Okay, what happened?
So when do you use this formula?
Why will?
So when do you use this formula? The AE.
According to this given equation, how much will 100 grams of radon? So the value A is 100. So what will happen? Radon 222 decays at a continuous rate of 17.3% per day. How much will 100 grams of radon 222 decay in 3 days? So the initial starting value is 100 grams. That is, the value A is 100 grams, 100 milligrams. So A is 100. Then E, we have that value. It's a fixed value. And for the, what we have, so here in 3 days, no, 3 days in the sense. So the value of R is 0.13173, that is 17. Okay, let me write. Okay, so here the initial value, starting value A is 100 milligrams. Then the continuous rate is 17.3%. No, 17.3% means there we have 0.13, right? 0.13173. But this one is decays. Decays means decreasing. Then this rate, what will happen with the rate? Rate gets
Negative.
negative. Yeah, rates get negatives. Then here they have set it to ask us to calculate it in 3 days. Now 3 days in the sense x is equals to 3. X is equals to 3 days. So now you can put this to the given function. We have to have the final value after 3 days, that is A times E minus 0.173 173 to the power 173 into 3. Now this 3 is the number of years. Here we have the decay rate. A is 100. E we have the value 2.714828. Then we can have the value. We can have this value. Okay. Is it okay? Okay. Then I think the rest of these ones are actually the theories. So you can try this one as homework and the example 12 also as homework. Do all these questions. And also then they have uh, summarized the entire section what we have already covered. We did percent growth and we did about exponential functions. There we did finding formulas, interpreting equations, graphs. So we already covered these ones, and also the exponential growth and the decay we discussed, compound interests, annual percent yield, and also finally the continuous growth as well. All these ones we already completed. So then you have the exercise. This one, try it now answers. They have given the answers. You can check for the answers as well. Then you need to do this section 4.1 exercises. This one is homework. Okay?
It's this one.
Oh, yes. You have this, I sent you this entire tude, right? The chapter.
Yes.
Oh, okay. Then you can
But you
complete
didn't
it.
send
Huh?
like yesterday's
Ah,
uh
yeah, okay. I'll send that one. Yeah, I'll send that. And also the recordings links as well. I did the conversion, but I didn't upload that to the YouTube. I'll upload that one and send the link. So here we have the section 4.1 exercise. So you can do the entire exercise, this one and this entire one also as homework. So the section one, for this one also as homework. Oh yes, so many homeworks. This one also has homeworks. So then you can do these ones as homework. Now we have the 4.2 graphs of the exponential functions. I'll move to the graphing part as well. The second topic, it is 4.2, the graphs of exponential functions. So now we already know how to draw a linear graph, no? So if we have 2 points, two coordinates of 2 points, then we can draw a line as well. Or else if we have the gradient or else if we have the equation of a line, then we also can draw that graph. Like with linear functions, the graph of an exponential function is determined by the values for the parameters in the function's formula. So if it's a linear one, then the equation is y is equals to mx plus c. Okay. Now, so the entire linear graph, I mean that line, we can describe this line by using this gradient as well as the intercept. So anyway, how we determine about that line, that is all from this gradients and the by using these gradients and the interceptions as well. Now, to get a sense for the behavior of the exponentials, now we are going to draw these exponential curves. So, for example, let's assume we are going to draw the graph of y is equals to 2 to the power of x. Now, can you draw this graph and send to me now? The first one, this one is an exponential graph. Why? X is in x. We have used this x, the variable x or the input value x as the exponent. Here we have the exponential graph. Okay, here we have the exponential graph. Then first task is you have to draw this exponential graph. That is y is equals to 2 to the power of x. So then what you can do, you can draw a data table. Okay, you can draw a data table and find few data points. Take some negative values. Then in the middle we have 0, and also take some positive values as well as x, and then find out the respective y values, and then draw the data table and then draw the graph. Do that one. Function of x. This is the equation. Function of x is equals to 2 to the power of x. 2 to the power of x.
Where do I send it?
Yeah,
Hello.
the graph. Yes. You didn't send me, right? I didn't get no. Let me check. Still, I didn't get. How the curves work? So were you able to draw? You didn't send me either. No, still, I didn't receive.
Oh, I do.
Okay.
Like this.
Okay. I received. Drawing graph. Yes, yes. See, now the graph is looks like this. The curve will be like this. So here, so they also have listed all the data points values in a data table. So you also will receive these ones. If it's minus 3, then 1 over 8, minus 2, 1 over 4, minus 1, 1 over 2. Likewise, the data table will give like this. And notice that this function is positive for all values of x. You can see, though we input negative values, minus 3, minus 2, and minus 1, anyway the y value is a positive value, right? Oh, 1 minute.
Yeah.
Hello? Oh, so here, what will happen? This function is positive for all values of x. For all the values of x, so the y values are positive. As x increases, the function grows faster. You can see the curve. There we have kind of a rapid growth when the x value increases on the y values. The rate of change increases. As x decreases, when the x values are getting decreased, the function values grow smaller, approaching 0. This is an example of the exponential growth. If it's an exponential growth, then the curve will be like this. Is it clear?
Yeah.
Okay. Now, on that same graph, can you draw gx is equals to half to the power of x? I'll tell you why the reason is on the same Cartesian plane, just draw this graph as well. Half to the power of x. Okay. First you need to draw the data table. Okay. And then you need to, sorry? Sorry?
Nothing.
Okay. So on that same plane itself, I just wanted to show you the inverse thing. So that's why I just ask you to draw this function gx is equals to half to the power of x. So the earlier curve was looks like this. Okay, now let's see for this one how it works. On the same plane.
Sent.
Yes, I received. Ah, so now you can see what will happen here. This function is actually half to the power of x now. So half to the power of x. Half, you can rewrite it as 2 to the power of minus 1, right?
Yeah.
Because here we have 1 as for the, what we call the denominator's power. So if I get this denominator to up, then there we have 2 to the power of minus 1. Then we have x here, which means here we have 2 to the power of minus x. Now what's happening? 2 to the power of minus x curve looks like this, and 2 to the power of x curve looks like this. See the difference. Here we have 2 to the power of x. Here we have 2 to the power of minus x. So here we have the positive power. Here we have the negative power. Now you can see the difference. Note, this function is also positive for all values of x, but in this case, growth, grows as x decreases and decreases towards 0 as x increases. So for this function, when the x value grows, the y value also grows. And when the x value decreases, then the y value is getting much closer to 0. But for this one, 2 to the power of minus x, when x value getting increased, the y value getting much closer to 0. And when the x value is getting decreased, here the y value getting increased a lot. This is an example of exponential decay. This one is exponential growth. You can see this one is exponential growth. This one is exponential decay. Okay, is it clear for you?
Yes.
You may notice from the table that this function appears to be the horizontal reflection of the fx is equals to 2 to the power of x table. This is in fact the case function of minus x. So here that's what I already explained. Okay, and then consider a function for the form abx. Now, our task is we had that exponential growth function. Exponential growth function, what we had was a times 1 plus r to the power of x. This one was our exponential growth equation. We can rewrite it as ab to the power of x as well. So consider a function for the form of ab to the power of x, since a is the initial value as what we learned in the last section, and then is the function value at an input of 0. A will give us a vertical intercept of the graph. From the graphs above, we can see that an exponential graph will have a horizontal asymptote on one side of the graph and can either increase or decrease depending upon the growth factor. So this horizontal asymptote, if you check for this one, here we have a horizontal asymptote. What is the horizontal asymptote we have? For these two
Y
graphs,
equals 0.
y is
Y,
equals to 0. Yes, y is equals to 0 is the
y equals
horizontal.
0.
Yes. Horizontal asymptote. We can see that the exponential graph will have, okay,
Y,
yeah, this one is the horizontal exponential horizontal asymptote. So the horizontal asymptote will also help us determine the long run behavior and is easy to determine from the graph. So the graph will grow when the growth rate is positive, which will make the growth factor be larger than 1. When it's negative, the growth factor will be less than 1. Okay, that's fine. Can you draw this one? Can you draw fx is equals to 4 times 1 over third x? Sketch this graph. Sketch this graph. Sketch this graph. Can you draw this one? 4 times 1 over third to the power of x. Mhm.
Wait, when it's 0, it's 4, right?
When x is equals to 0, the y
And y
value
is
is 4. Yeah. Done?
yes.
Okay. How the curves looks
It's a decay.
decay. Yeah, it's a decay. So when x is equals to 0, then we have the y-intercept, right?
Simple.
Yeah, when x is equals to 0, we have y is equals to 4. There we have the, okay, you have already sent me the graph. Yes, that's correct. So now, for the example 1, the graph will have a vertical intercept. So they have a vertical intercept at 0, 4 and pass through the point when x is equals to 1, there we have 4 over 3. Since so the value b is less than 1, b means what? So this one, right? The value b is less than 1, the graph will be decreasing towards 0. That means actually there we have a decay. So the a value is greater than 0, the graph will be concave up. So we can also see from the graph the long run behavior. When the x values goes to the positive infinity, what happened to the y values? When the x goes to the positive infinity, what happened to the y values? Y values
0.
are getting much closer to 0. And also, when the x values are getting closer to negative infinity, what will happen to the y value? Y value
It will.
it's increasing and it will be going up as positive infinity. So that's what they have explained here. So when they ask you to draw a graph, you have to give all these points. Those are the things they have theoretically explained here. When the value b is greater than 1, then the function is a decreasing function. When the value b is in between 0 and 1 as 1 over 3, okay, then we have a decreasing function, then the function will be a decreasing function. So the horizontal asymptote, we have that horizontal asymptote at y is equals to 0. And also, if the initial value is a positive value, then it will concave up. Okay. If the initial value is a negative value, if a is less than 0, then it will concave down. And also the domain of the function, the y value, domain means actually the x values, no? So the domain of the function is all the real numbers, either the positive real numbers, 0, and also the negative real numbers, all the real numbers, and the range is, so no values in negative side. All the y values are in positive sides. Therefore, we can say the range of the function is 0 to positive infinity. When sketching the graph of an exponential function, it can be helpful. So remember that the graph will pass through the points. So what will happen? Because of that, we can say that those graphs will pass through the lines 0a and 1ab. Okay, those are the 2 points. Is it clear for you? Then is it
Yes.
okay? Then also you should be able to explain these ones when the b value means here we have 1 over 3. No? B value is greater than 1 now, then x goes to the infinity, y value also goes to the infinity, because if the b value is greater, here we have the summary. So if b value is greater than 1, then we have a increasing function. Increasing function means the function looks like this, okay? And when x goes to the positive infinity, y value goes to the positive infinity. When x goes to the negative infinity, y values are getting much closer to 0. If the b value is in between 0 and 1, what will happen? There we have when x value is getting when x value is going to the positive infinity, then the y value becomes getting closer to 0. So there we have the decay, decreasing function when b value is in between 0 and 1. Is it clear for the whole set of graphs? That's the only thing you need to know of these graphing parts, exponential curve graphing parts. Is it clear for you? Are you sure?
Yes. Yeah.
Now, what they are saying is to get a better feeling for the effective of A and B on the graph, examine the sets of graphs below. The first set shows various graphs where A remains the same and we only change the value for B. Now see, by looking at these graphs, here we have 1.5 to the power of x, 2 to the power of x, 3 to the power of x, 1 over 3 to the power of x, 1 over 2 to the power of x, 0.9 to the power of x. See all these graphs and tell me what has happened here when we are changing the value b to these curves. Explain me. So First, explain these ones 3 to the power of x graph, 2 to the power of x graph, and y to the power of x graph. There, x remains same, only 3 to 1.5. The base gets changed. The base got changed. So for those kind of ones, what has happened for the curve?
It get more faster to animate.
Yes, yes, yes. So here we have 1.5 to the x. Here we have 2 to the power of x. Here we have 3 to the power of x. Now what has happened to these ones? 1 over third, 1 over 2 and 0.9.
The smaller it goes to.
Yes, yes, yes. When that base value getting much more closer to 0, closer getting decreased actually. Here we have 1 over 2 means 0.5. Here we have 1 over 3 means 0.03, 0.3. Then when the value getting decreased, it will again much closer to the y-axis. It's getting curved like this. Okay. Here, then we have 0.9 to the power of x. Then there we have a curve like this. Okay. That's how it works. Notice that the closer the value of b is to 1, see, here we have 0.9 to the power of x. It's getting much more closer to 1. Then notice that the closer the value of b is to 1, the less steep the graph will be. Less steep the graph will be. In the next set of graphs, a is altered. So here we altered only value b. Here we altered the value b. Okay. But for the next few examples,
Yeah.
the b will be remaining same.
The B means like the
B
1.2,
means
right?
yes, b means 1.2, b means 1.2, a means 4, 3, 2, those ones, the initial values. So now the b fixed, only a differs.
What if there's no A?
Huh?
Like there's no A on the 1.2x.
I didn't get you, sorry.
Like below there's no A.
Yes. So this one.
Yeah.
This one, a is equals to 1. That's why.
Oh,
A is equals to 1. That's why there we don't have A. So here 1.2 to the power of 5. So if I write it like this, 1 times 1.2 to the power of x, 0.5. Okay, now see, now how it works. When the value A is increased, so you can see from that value A, we can decide where this has its vertical intercepts. If the A value is 0.5, then it has the vertical intercepts at 0.5. If it's 1, then there we have the vertical intercepts at 1. If it's 2, then we have the vertical intercepts at 2. If it's 3, then we have the vertical intercepts at 3. Likewise. Is it clear?
Yes.
Notice that change in the value for A changes the vertical intercept. Since A is multiplying the b to the power of x term, A acts as a vertical stretch factor, not as a shift. Notice also that the long run behavior for all of these functions is the same because the growth factor did not change and none of these A values introduced a vertical flip. Only thing is it's changed the vertical intercepts. The rest of these ones are the curvature and rest of these ones are it's same. Is it clear?
Yes.
Okay. Now, what you have to do this example 2 as homework. What you need to do is you draw all these functions on a same graph itself, same Cartesian plane itself. Okay. This one as homework, this one also as homework. Then we'll do the transformation of exponential graphs next day, tomorrow. Okay. And you have the previous 4.1 section. We have that. You have that exercise as well, so that you need to complete all these ones. So, are we doing applied maths today as well?
I
What do you
mean,
think? What do you think?
I don't know what. Ask my
Okay.
dad.
Okay. You just asked from dad. I think I told him that we'll do like 4 hours today. We'll have a short break. I mean, even I have to take my dinner as well. So let's have like, if we are doing the applied math today, um, then what we can do, we'll take a 20 to 30 minutes break and then start around 10:30. Within another 20 minutes, we can start the applied math one and then complete that one. You just ask and confirm me, that's fine. Okay?
You can ask on what.
Sorry?
You can ask on WhatsApp.
Okay, I'll ask. Okay, I'll ask. Okay. Anyway, I told him that we will be continuing like this. Okay, you also have to ask from WhatsApp.
You can ask like
Okay, okay,
the conflict.
okay,
Thanks.
okay. Let me ask. Okay, I'll ask and confirm you. Okay,
Mm.
okay. Thank you so much. If so, if we are doing, then we'll start it like another 20 minutes again. Okay. Okay, let me ask that one. Are we doing the applied today? Shall we start it in another 20 minutes after a small break? He didn't reply me. He didn't reply me. Still, you can just connect with him and get the confirmation. I also already sent him a WhatsApp chat. So if we are doing, then we'll meet in another 20 minutes. That's why with the same link, okay? Hello?
He'll
Okay. Then, uh, okay. Now he's typing. Let me check. Let me check what he's telling. Yes, we can have a class. Okay, then in 20 minutes, we'll meet from the same link. I'll tell you, okay? Thank you. See you in another 30 minutes, 20 minutes. Okay, see you in another 20 minutes. Thank you.